In this video, we work exercise number 99 from the Larson Calculus text, 10th edition. It's just another application of exponential functions. We've done so many applications involving compound interest. We'll see in the next few problems that there are other applications that don't involve compound interest at all. And this is one about timber, which is not something that I'm very familiar with, but we can learn about it from the problem statement. So we're told that V of t is the yield V in millions of cubic feet per acre for a stand of timber at age t. And so this is giving us some number of cubic feet of timber per acre, t years after some reference point. We're asked to find the limiting volume of wood per acre as t goes to infinity. So that's just the limit as t goes to infinity of this function. Now the exponential function is continuous. Since the exponential function is continuous, we can bring that limit inside the exponential function. So this is equal to 6.7 times e raised to the limit as t goes to infinity of negative 4.8 divided by t. So if we can take the limit of this and we get a finite number, and that finite number is in the domain of e, then you're allowed to just compute that limit, plug it in, and then that's going to be the value of the limit of this function. Well, as t goes to infinity, negative 4.8 divided by a really large number is a really small number. So this is going to go to 0. We'll have 6.7 times e to the 0, which is 6.7. So what does that mean? As t goes to infinity, or let's just say as t increases, sometimes they'll say in math class, increases without bound. So it just keeps increasing. The volume of wood per acre approaches 6.7 million cubic feet. Or we could say the volume approaches 6.7 cubic or million cubic feet per acre. Maybe this per acre should be over here instead. I'm actually not sure. Now we're asked to find the rates at which the yield is changing when t equals 20 and t equals 30 or 60 years. Basically, that's just asking us for a derivative at two particular values of t. So we'll compute the derivative of this. It's actually relatively simple to do. And that negative 4.8 divided by t, we can rewrite as negative 4.8 times t to the negative first power. And then we see that we're just going to use the chain rule. We've got this function inside the exponential function. So when we use the chain rule, we'll get the derivative of the outside function evaluated at the inside function, so you don't do anything to it. And then you multiply by the derivative of the inside by the chain rule. And if you're taking the derivative of a constant times t to some power, well, you just get that constant times the power times t to the 1 less power. A negative times a negative is a positive, so this is going to be 4.8 times t to the negative 2, which is 4.8 divided by t squared. So what you end up with is 6.7 times 4.8, whatever that is, times e to the negative 4.8 divided by t, all divided by t squared. And that t squared is coming from that t to the negative 2 that's multiplying this function. I actually don't know what that number is. One thing that I noticed right away is that I've just got a number times an exponential, which is always positive, divided by t squared. This is undefined when t equals 0. The original function was undefined when t equals 0 as well. And this is always positive, and this is always positive, so v prime is always positive. So that means that yield is always increasing. Now, if we're evaluating this at t equals 20 and t equals 60 years, we just substitute 20 here. So you'll have 6.7 times 4.8 times e raised to the negative 4.8 divided by 20, all divided by 20 squared. And this is a rate of change of volume. The rate of change of the yield in millions of cubic feet per acre. Per unit time, where T, I believe, is time in years. So if T is measuring time in years, we'll just say per year. So that's going to give us a number. We will evaluate that, find out what that number is online. And we'll do the same thing at T equals 60. So you just have this expression, and it's e to the negative 4.8 divided by 60, because you're substituting T equals 60, divided by T squared, which is 60 squared. It has the same interpretation, we're just going to have a different number. And this is the rate of change of the yield in millions of cubic feet per acre per year, 20 years into the future. And this is the rate of change of the yield in millions of cubic feet per acre per year, 60 years from some start date is what I imagine. T equals 0 probably represents the start date. So let's look at those numbers online. So this is our function f of t. It actually has two branches. It's undefined for t equals 0, and it has a branch when t is negative and a branch when t is positive. But assuming that t is the age of this stand of timber, which is a term I'm not familiar with, I would assume that t is greater than 0. So v of t is just that function when t is greater than 0. So we're talking about this piece. And even though it's not necessarily obvious, the limit of this function as t approaches 0 is actually 0. Because if I take t and I make it a tiny positive number, negative 4.8 divided by a tiny positive number is going to be a large negative number. So every time you divide by like 1/1,000,000th, you're multiplying by 1,000,000 essentially. So you're going to get this negative 4.8 times 1,000,000 at t equals 1,000,000th. Well, if you raise e to that large negative power, you're going to get a number that's very small. So that number, that exponential with the negative exponent, is getting closer and closer to 0. So as t approaches 0 from the right, v of t is approaching 0. So we've got that open circle at 0, 0 there. But otherwise, the graph looks like this. We said the limiting volume of wood per acre as t goes to infinity was 6.7. Because the limit of the exponent as t goes to infinity is 0, e to the 0 is 1, so we end up with 6.7. And you'd say, well, what does that mean? That means as x goes to infinity, or as t goes to infinity, the yield approaches 6.7 million cubic feet per acre. Sometimes you'll see problem statements that say, what is the yield after a really long time? Or something like that. When they say after a really long time, they're usually just saying that t is going to infinity, and you compute that limit. And if we graph y equals 6.7 and we graph the original curve, we can see that that curve, the y values on that curve get closer and closer to y equals 6.7 as t gets very large. Now we were also asked for, excuse me, the rates of change when t equals 20 years and t equals 60 years. So we take the derivative using the chain rule, and we've already done that on paper. So we have 6.7 times the exponential times the derivative of the inside, which is that 4.8 times t to the negative 2. If we multiply the 6.7 and the 4.8, turns out we get 32.16. And if we write that t to the negative 2 as a t squared in the denominator, this is our sort of simplified form of that dv dt. And we're, again, only interested in it for t greater than 0. So here's the b prime. It's very small. We see that it has a local maximum or a relative maximum somewhere between 0 and 5. Oops. So essentially, the yield, the increase in the yield sort of maxes out at that particular t value. And then the rate of change of the yield starts to decrease. So it's basically when the graph goes from concave upward to concave downward is at that maximum there. Now, if we evaluate this function v prime at 20, we did that on paper and simplify, we get this 0.063 number. So that's telling us the yield is changing at a rate. of approximately 0.063 million, or 63,000 cubic feet per acre per year when t equals 20 years. And if we want to, we can graph that point. Okay, that's actually the yield. So at t equals 20 years, the stand of timber yields 5.27 million cubic feet per acre. And that yield is changing at a rate of 0.063 or 63,000 cubic feet per acre per year. So we're still getting 63,000 cubic feet per acre, but that yield is getting smaller and smaller as t gets larger and larger. And we don't have to graph a tangent line, but I always like to graph a tangent line. So if we want to, we can see that that's what the tangent line looks like there. Now we're also asked about the yield when t equals 60 years. If we evaluate v prime at t equals 60, we get 0.082. So this tells us that the yield is changing at a rate of approximately 0.008 million, or 8,000 cubic feet per acre per year. So it's decreased, the rate of change itself has decreased a lot. It's come from 63,000 cubic feet per acre to cubic feet per acre per year to 8,000 cubic feet per acre per year. So it's basically saying that we're not getting nearly as much wood, as much volume of wood at 60 as we did at 20. And we can see that if we plot the points. When t equals 60, the output, the yield is 6.18 million cubic feet per acre. And then the rate of change is about 8,000, or 0.008 million, which is the same as 8,000. And if we want, we could graph a tangent line. That tangent line would give us a linear approximation of that yield, and it would be a good approximation as long as we're close to about 60 years. And I don't know why, but I graphed another tangent line. I always do that. I don't know. Probably because we graph way too many tangent lines in Calculus 1. Like, look at the tangent line move. I think it's fun. Yay. It's a little bit silly. And we talked about the fact that the limit as t approaches 0 of the function is 0, because the exponent goes to negative infinity, and e to a very large negative power is 0. All right, so that is our timber example. We have lots of other examples at the end of this section. I highly recommend that you just check out those examples in section 5.5. There are some that are really interesting, with interesting applications and then rates of change. The functions themselves are relatively simple and derivatives are easy to compute. But the way that we apply exponential and logarithmic functions in our daily life is pretty cool. So I hope you'll check that out and enjoy it.